Hello everyone, I'm Wei Chen from the University of Hong Kong. Today I'm going to introduce our paper about insider threat prediction based on unsupervised anomaly detection scheme for proactive forensic investigation. Let's start with the motivation of our research. According to a white paper published by International Data Corporation, the global data volume will grow to 175 gigabytes by 2025. The data has become the critical resource in the world. However, a direct consequence is a significant increase in digital crime, which affects both the society and individuals dramatically. Therefore, digital forensic research on big data has shown its vital role in recent years. And with the statistic information collected by the breach level index, almost 214 records are compromised every second all over the world, and around 40% of data leakage is induced by insiders. Insider threat has led to great damage all over the world. In order to prohibit insider crimes effectively, insider threat detection, investigation, and prediction problems have become attractive for researchers. Traditional digital forensic investigation adopts a reactive approach. Analyzing and interpreting the digital evidence are performed after a crime has been committed. Even if the insiders can be detected, they have already caused huge damage to the organization. What's more, traditional digital forensic investigation always take use of statistic estimation or rule-based methods, which are not fit for solving the complex insider threat situations. With the prevalence of deep learning technology, lots of effective anomaly detection methods have been proposed. Nonetheless, most existing methods are supervised ones. They need the labels during training, which is impractical in real cases, and it is infeasible or ineffective to label the large amount of data manually. Moreover, the detection performance also depends on the quality of feature engineering. And due to the imbalanced datasets in anomaly detection problem, existing solutions for anomaly detection always encounter the notorious problem, the relatively high false positive rate. Last but not least, note that not all the anomalies are actual insider threat actions, and some normal actions would have abnormal appearance. For example, some behavior violations due to sudden rule change. Insiders would also deliberately hide their malicious behaviors to make them look like normal ones. Anomaly detection methods cannot be applied in insider threat prediction problem directly. In order to solve the above dilemma, we propose our end-to-end unsupervised insider threat prediction framework for proactive forensic investigation. Before introducing our design, I will give a brief introduction of some preliminaries. The basic autoencoder is a special kind of feed-forward deep neural network which can be divided into two parts, encoder and a decoder. The objective of this model is to reconstruct the input in the output layer. It is widely used for anomaly detection. They first use the labels of the data to select only normal data in the dataset, and only use this normal data to train this autoencoder. Although the training process is unsupervised, the whole process is semi-supervised. In this paper, we modify this model, and our whole process is real unsupervised. Gaussian mixture model is commonly used to estimate the distribution of the data. To make it simple, we can imagine in the two-dimensional space. We usually use Gaussian distribution to estimate the normal distribution of the data. The right upper figure shows an example of multivariate Gaussian distribution in two-dimensional space. Then we extend it into high dimension. We have the below example. In this work, we propose an unsupervised anomaly detection scheme. This is an overview of our scheme. It is Cascaded autoencoders purification-based joint optimization scheme. We call it CIOS for short. It comprises several autoencoders and a basic feed-forward fully connected deep neural network. We call it DNN for short. We cascade several autoencoders and to act as the data purification component, which is capable of filtering out the anomalies from the unlabeled data. After case autoencoder filter, the data can be recognized as pure enough normal data with negligible anomalies. Then one more autoencoder is utilized to act as a dimension reduction component, and DNN is used to estimate the parameters of Gaussian mixture distribution. The last autoencoder and the DNN is trained together to construct the joint optimization network. In detail, the cascaded autoencoder filters act as unsupervised data purification component. The training data is fed into the first autoencoder. After training, we sort the data according to the reconstruction error between the input and the output. Here, we use mean absolute error as the measurement metric. Then we drop out a percentage of the data with a larger reconstruction error as a potential anomalies. The remaining data is fed into the second autoencoder and repeats the former steps. After k rounds of autoencoder filtering, we can get the dataset with only normal data. Actually, we have demonstrated this unsupervised data purification effectiveness both theoretically and empirically in our previous paper. And this experiment, we get our best performance in which k is set to 5 and r is set to 20%. Here we go to the joint optimization network, which is consists of the last autoencoder and a DNN. The DNN can be expressed as this function, where P is input samples, W is weight matrix, B is bias vector, sigma is the softmax activation function, and P hat is output, which is a C-dimensional vector used for mixture membership estimation. We use the output of DNN to estimate the parameters in the Gaussian mixture distribution with C Gaussian components. Denotes the mean and covariance matrix of the C Gaussian component as mu C and sigma C. And the probability that a sample belongs to the C Gaussian component as alpha C. We estimate the parameters in Gaussian mixture model as these formulas, where n prime is the number of input samples, PIC hat is the probability that sample I comes from the C component. We connect the last autoencoder and the DNN and train them jointly. The input of the last autoencoder is original input features, and the input of the DNN consists of two elements. One is the middle coded layer of the last autoencoder. Another one is the reconstruction error between the outputs and inputs of the last autoencoder. The objective function for joint optimization network contains the loss function of autoencoder and the sample energy of DNN. And EPI is the sample energy, which is negative log probability of observing the input sample PI. This joint optimization is used to solve local minimum problem. For testing set, we calculate their sample energies as anomaly scores and call the probability of observing the input samples as appearance confidence, which we will use in the following steps. All the steps with anomaly scores larger than a threshold will be treated as suspicious anomalies. The threshold is set according to cross-validation step. In the following, I will introduce how we extend the proposed unsupervised anomaly detection scheme to the insider threat prediction problem. Before that, I will introduce the dataset we used in our experiment to show how our work can be utilized in practice. It is a collection of synthetic insider threat test datasets published by CMU. It is only available datasets for public access. It is several versions. We use the latest version, R6.2, which contains the most complex situations. There are a total of around 120 gigabyte system operation log files recording 4,000 employees' actions about device connection, email communication, web browsing, file operating, and log on and log off activities within 516 days. Employees' metadata information are also provided. LDAP directory and psychometric files store the functional information of the current employees in each month, as well as their Big 5 personality traits measured by the corresponding psychometric scores. This is the workflow of our insider threat prediction framework. What we have is the raw log files, as I mentioned before. We pre-process the dataset, and for each user in each day, a behavior sequence is generated. Each behavior sequence is a sequence of numbers, which represents the employee's actions chronologically. And after generating the behavior sequences, we feed it into BioSTM model to learn the behavior language of the employee's actions as an NLP task. After training, we use the last hidden layer of the BioSTM model as the extracted features, and the samples encoded by the extracted features are then fed into seeders. After the former training steps, when new behavior records come, they will go through the former steps, and seeders can recognize the suspicious anomalies and give out an anomaly score for each sequence. With the help of Hypergraph correction model, the behavior sequences with the correction confidence less than a threshold will be predicted as the insider threat behavior sequences. Therefore, we can respond in real time and eliminate the insider negative influence as soon as possible. Let's go into the details. The first step is about how we pre-process the raw log files, encode them into the input of the BioSTM feature extractor. We combine the log entries from each log file on the per user per day basis and arrange them as behavior sequences according to the timeline. We investigate the user's daily behaviors in the context of this dataset and extract a total of 164 behavior numbered from 1 to 164 respectively, as listed in this table. Select one value in each row to construct one user behavior encoded with a number. For example, connecting a device in the office hour at weekday is encoded with 1, and the corresponding disconnect operation is encoded with 2, etc. For each user in each day, there is one behavior sequence after this pre-processing. A total of 1.3 million behavior sequences are generated. BioSTM is a variation of classical LSTM model. Being different with autoencoder, LSTM is not a feed-forward network. It has loops. During training, the input of the latter unit is related to the output state of the former unit. BioSTM still has the basic LSTM unit, and it has two directions, forward LSTM and backward LSTM. Given an input sequence, we use one-hot encoding to embed each vector BI to a vector VI, and then feed into the BioSTM as one of the input samples. The BioSTM model can predict the output of VI as YI, and the loss function is binary cross entropy between VI plus 1 and YI. After training, we use the hidden states of the last hidden layer as learned features. Users metadata features, for example, rule, supervisor, psychometric test score, etc., are concatenated with the learned features to form the final extracted features. Then all the samples encoded with these extracted features are fed into our seeders. Then we apply our seeders to do insider threat detection and prediction. The outputs of seeders contain all input behavior sequences, probability of them conforming to Gaussian mystery distribution, and the set of suspicious behavior sequences if their corresponding anomaly scores are larger than the threshold. The output probability is considered as appearance probability of the corresponding samples. Through experimental evaluation, we can catch almost all the insider threat behavior sequences through our formal steps. However, because we would also drop some parts of normal data during the data purification process, there may be not enough normal data to estimate the Gaussian mixture distribution, which would lead to high false positive rate issue. So we add a hypergraph correction module to improve the detection and prediction accuracy. Hypergraph is a special kind of graph. Compared to traditional graph, hypergraph also has vertices and edges, which we call them hyperedges. One of the differences between the hypergraph and the traditional graph is that one hypergraph can contain more than two vertices. Take figure 4 as illustration. E1, E2, and E3 are hyperedges which contain more than two vertices. As this is a pure mathematical problem, due to the time limitation, I will skip the complex mathematical definition and the detection and introduce how we use spectral hypergraph partitioning to help us distinguish the true positive from false positive insider threats. After the spectral hypergraph partitioning, we can get two partitions, and we call the partition with smaller size as hyperabnormal partition HA, and the partition with larger size as hypernormal partition HN. The records in HN gets the correction confidence with the value of phi multiplying corresponding appearance confidence. And those ones in HN get the correction confidence with the value of tau multiplying corresponding appearance confidence, where beta is the corresponding appearance confidence we obtain in our proposed seizure scheme. Hence, we can give out a belief confidence of each recognized species anomalous sample being the actual insider threat. For users without domain knowledge, we set a threshold eta for them to make a final decision. Where eta is set according to cross-validation procedure, they can predict the behavior sequences as actual insider threats if their corresponding correction confidence are less than eta. We evaluate the anomaly detection performance of our seizures on some public benchmark datasets. Figure 5 shows the filtering performance of our cascaded autoencoder filters. Lines with different colors represent the model working on the datasets with different anomaly ratio. They are showing the decreasing tendency of remaining anomalous percentage in the remaining training sets autoencoder by autoencoder. They also show the value of K required to filter out all the anomalies in the training set. One autoencoder is enough to purify the training set when the anomaly ratio is less than 5%. And even if the anomaly ratio increases to 40%, our scheme still has the capability to purify the data with unsupervised manner. For the anomaly detection performance evaluation, we use a standard evaluation matrix. Recall precision and F1 score in the table 1, 2, and 3. For each column, the best result is highlighted in bold. Seizures almost achieve best performance, although one class's VM gets slightly higher precision. It suffers quite low recall and F1 as sacrifice, which are unacceptable in real cases. About the insider threat prediction performance evaluation, we use 3 metrics: recall, false positive rate, and AUC. Recall shows the ability of discovering the actual insider threat behavior sequences. For insider threat prediction, it is critical to discover all the insider threats in the organization, since even one overlooked insider action would bring huge damage to the organization. Therefore, recall, also the same as the true positive rate, is the most important metrics for insider threat prediction performance evaluation. Meanwhile, too much false alarms will cause much workload for digital investigators. So false positive rate is another vital metric to evaluate the methods. As true positive rate and false positive rate is a pair of trade-off, we also look at the AUC score, which indicates the area under the ROC curve, where the horizontal axis represents the false positive rate and the vertical axis denotes the true positive rate. The best metric results have been labeled in bold in Table 4. Through experiments, we demonstrate that our insider threat prediction framework outperforms other state-of-the-art baseline models. The false positive rate in the proposed framework is less than 1/4 of the smallest false positive rates achieved in other baseline models. Additionally, our insider threat prediction framework requires higher recall and AUC score than the state-of-the-art deep learning methods. About the conclusion, in this paper, we propose a novel general unsupervised anomaly detection scheme based on cascaded autoencoders and joint optimization network. Our core idea is to utilize cascaded autoencoders to do data purification among unlabeled data, then jointly optimize the dimension reduction and the density estimation network to avoid suboptimal problems. On the basis of this scheme, we design an end-to-end insider threat prediction framework for proactive forensic investigation, through which we can make real-time response to prevent the harmful influence of insider threats. We extract the scalable feature representation automatically through the data-driven BioSTM feature extractor, waiving the time-consuming feature engineering work. Additionally, a hypergraph correction module is applied to solve the commonly existed relative high false positive rate problem in insider threat detection. We evaluate our scheme and framework on public benchmark datasets. The experiment demonstrates that our models outperform state-of-the-art unsupervised methods. About our feature work, for automatic feature extraction, we use BioSTM as a feature learning model, which is capable of catching temporal relations between actions. However, the context of the actions is also important for feature extraction. So in the next step, we will try to use BERT learning model as the feature extractor to see whether the performance can be raised or not. Till now, most existing deep learning solutions for anomaly detection problem can only work for structured data and ignore the underlying relations among the data. Our next work will take use of graph neural network to improve the performance. Since Autoencoder has shown its strong capability in unsupervised learning and dimension reduction, and there are already many variations for Autoencoder, we will try to utilize its advanced variations for automatic feature extraction and dimension reduction for improving the performance and accelerating the training speed in our future work. That's our presentation today. Thank you.